Coffee pulp is one of the most abundant residues in coffee production. Although it seems harmless, its high organic load makes a real environmental challenge for small farms. In our PBL, we set out to transfer this waste into value using enzymatic hydrolysis and to determine which reactor design would be truly viable in a real coffee farm. Coffee pulp represents about 40% of the coffee cherry. When it's accumulated, its fermentation produces odors, attracts pests, and contaminates water sources. But the most important restriction is practical. Farms do not have industrial infrastructure. That constraint shaped every design decision we made.
Experimental base. We designed 35 microassays to model the hydrolysis kinetics. From glucose production curves, we calculate the initial velocities and build the Michaelis mental model. Our kinetic parameters were Pmax 0.944 gram per liter mean and Km 57.04 gram liter. These values describe how the enzyme behaves and determine how large each reactor needs to be. We test inhibition models to back the statistics, confirming the Michaelis mental without inhibition was the most accurate and consistent for design. Process context. The overall process includes pulp collection, preparation, extraction, conditioning, and the hydrolysis itself. But for the reactor design, the critical stage is the enzymatic reaction, where concentration limits, viscosity, and reaction rate define the feasibility of each configuration.
We use the exact same basis for the three reactors, the same biomass load of 63,360 kilograms per year, the same conversion of 22.8%, and the same kinetic parameters. This made the comparison fair. Batch required around 508,040 liters. At that scale, viscosity and mixing limitation become critical, making operations slow and energy intensive. Feed batch required about 6,500 liters. Despite the better concentration control, the final volume is still too large for the farm. The CSTR, however, needed only 64 liters because it works continually at the maximum feasible concentration of 80 grams per liter. It avoids viscosity problems and maintains a stable reaction rate. It can process the internal biomass in 319 days, leaving 26 days available for maintenance.
Selection. When we consider reaction kinetics, annual productivity, mixing condition, energy use, and real farm constraint, the conclusion becomes clear.
The CSTR is not only the best option, it is the only reactor that realistically fits the context of a coffee farm. It is compact, efficient, simple to operate, and matches the kinetic behavior of the system.
Impact and closing. With this design, we offer more than just a technical solution. We propose a sustainable model that reduces environmental impact and opens the door to value-added products derived from the pulp. This project demonstrates how biochemical engineering can turn challenges into opportunities. So keep this in mind. When we have a problem, we just have to think how to solve it in the best way. Thank you.